So the next topic I want to talk about is what diffraction pattern would you get, not from a square or rectangular single opening, but what if it was circular? Um, so basically now instead, if I kind of draw more of a 3D drawing. So now we've got this circular aperture, and we've got to still have a plane wave coming through. But then what's going to show up over here on the screen on the other side? So it's a single slit. It's a single aperture diffraction problem. So it's going to be very similar to what you would get with what we did before, the single slit, a single rectangular aperture, where, because of Huygens' principle, the light would then diffract through the opening, and then the wavelets would interfere with each other, and so you get this kind of self-interference pattern going on the other side on the screen over here. So what you would find is really, you would find a central maximum. Actually, let me make the screen bigger. What you would find is you would find a central maximum, and then you would find maxima and minima, which would then end up look like concentric rings. So that's what's going to show up over here on the other side on the screen. So you would see a similar pattern. You would see a bright central maximum, a minima, dark rings, but then you would see bright rings and dark rings and bright rings. So the derivation for this, again, is a little bit more complicated. It's not even really treated in an introductory textbook like Halliday, Resnick, and Walker. So the result that you would get for the minima, so you have destructive interference. So this would produce the dark minimum bands. And what you would see is that you would have d sine theta, where d is the diameter. So it's the diameter of the aperture. Is equal to some integer m. So depending on which dark band you're in, the first one, the second one, the third one, the wavelength of light, and then in front of this, you would get a factor of 1.22. So you get a result which is very similar to all the rest of the diffraction or these single slit, double slit problems that we've seen before, except for now you've got just a factor of 1.22 in front of it. The question is, where does that factor of 1.22 come from? And where it comes from is what I said in the previous video, and that is the intensity pattern that we're building over here on the screen is really a mapping in wavelength space of the geometry of the slit that you're actually going through. So what we're doing is we're doing a Fourier transform. And this time we're not transforming a rectangle. So before, if you remember, in space, my rectangle form, my single slit, so this is the slit right here, which in X has some width of going from minus a over 2 to a, and that, when you transform it, so this is my function of X, when I transform it into wavelength, what I get is the sinc function. So this is wavelength space, and what you get is something that is the sine of alpha over alpha, or the sinc function of alpha, where we said before alpha now is a function of wavelength. So the same thing happens here, except for the fact that now, because we're dealing with circles and not rectangles, we get a factor of 1.22 in front of the diffraction equation. And so, okay. Yeah. But the interesting thing that we can use from this circular aperture is that now we can kind of talk about how well can we resolve images through an aperture. You know, how well can you form them? So maybe if we take the example of a lens. So the lens is a circular aperture like this. And so light is now going to go going through that. And so basically the light that is now going to be traveling through this aperture, maybe the one light ray is going to produce an image over here, but that image is now going to have a diffraction pattern built into it. And then light waves coming through here are also going to be building, they also might have associated with them a diffraction pattern. And so this angle, the angle at which we can then resolve these images, basically comes from this equation. Sine of basically the smallest angle that we can make with the diffraction would be equal to 1.22 times lambda over the diameter of our lens, d, right there. So in this case, I'm taking the first dark band, m equal 1, and so if we apply the small angle approximation, sine of our resolving angle is approximately the resolving angle in radians, which is going to basically be equal to 1.22 times lambda over t. So if you think about it, if I have an object and I want to resolve that object in the crispest way possible, then I'm not going to have I don't want to make the aperture so small that I can't resolve it. Basically, the image is going to blend together the two diffraction patterns. So if I think about it, you know, the diffraction I'm making on one side makes this circular image with a bunch of rings on it. And if I have another that makes a diffraction which has some rings around it. So I can't really resolve anything if these two diffraction patterns merge together and kind of blend into a big blob. So basically the angular resolution, the ability to resolve objects, goes down to what kind of diffraction you're getting through the opening. So if I make the lens opening very big, if I have a very big lens, a very big D, compared to the wavelength of the light, and here we're talking nanometers for light, then, you know, usually then I can resolve it to a very, very small angle. It's only I start worrying that if I start to shrink down the size of the lens or the aperture, then now diffraction starts to play a role in how I'm forming the image, as opposed to just focusing with the lens. So the next thing we can consider is section 36-4, which basically talks about now what is the intensity pattern going to look like for a double slit experiment. So let's imagine now that we have this double slit. So we looked at it, and what we found is that if we had these plane waves diffracting through the double slit, then what I should get is a pattern of equal intensity peaks, where this is m equals 0, m equals 1, m equals 2, so forth and so on. But each of those slits in the double slit experiment can be considered a single slit. And so what I really see is a convolution of single slit intensity and double slit intensity, depending on the, how big the gap D is compared to the width of the slits A. So I can think of my slits now as having, each of the slits is a width A, and the distance between those two slits is D. And so what I get in the end is a pattern which looks like single slit diffraction, central maximum and smaller minima peaks. And then I have double slit diffraction, which is very narrow equal intensity peaks like this. And so if I put those two together, the combination of the two is the single slit diffraction combined with the double slit diffraction. Like so. So what you'll see is clumpings of very narrow bright bands from the double slit experiment, but then underneath a much larger distribution of the single slit diffraction. So therefore, if I look at the intensity of my double slit diffraction, so this is for the double slit experiment, the intensity function that I get would be, so intensity as a function of theta would be the max intensity that you would get from the incident light times cosine squared beta times the sinc function squared for alpha. So what are those alpha? Well, alpha we already said was pi a over lambda times the sine of the angle theta. It turns out beta is very similar. Beta is pi d lambda times the sine of theta, where again A are the slit widths and D is the slit separations, how far apart they are. So you basically have this convolution of the intensity from the double slit experiment. We have a convolution of the wavelengths mapped out from two slits, mapped onto the wavelength pattern you would get for the diffraction through each of those individual slits. So you can play around with it. You can play around with the, making the slits very narrow, which would make beta very small, which would then decrease the intensity. It would be very small. It would increase the intensity because you have a cosine. Or you could play around with the alpha, make those slits. You can play around with the distance between them. And you can play around with the actual width of the slits to try and modify this pattern, modify the intensity that you would get out of the two slits.